Hey, Unreal Fest. My name is Giovanni Pasteris. I'm a co-founder of Tempo Simulation. We founded Tempo Simulation just earlier this year. The first day of work was actually April 1st. That's my partner Pete sitting in the front row there. We provide simulation development services to robotics companies so that these robotics companies can train and test their models in simulation and then try to transfer that to the real world applications. But more on that later. Let's start our story with our first client, VRobot. So VRobot has big aspirations. You're looking at a product video here of theirs, and just on the surface, you might see this delivery robot, and you might think that's what they're all about. They're just trying to make a delivery robot, but that's not really the truth. In fact, they are trying to make the foundation model for robotic mobility to solve mobility for robotics in all domains. If you want to get your robot from point A to point B, VRobot intends to produce the model that will give you all the reasoning that you need to be able to get there. They needed simulation to start right from the start, and they knew they did. They already started to develop their own tools. But in order to go about developing these tools and starting down the path of creating this foundation model for mobility, they needed to start somewhere. So that's why they chose the starting point of creating a delivery robot. Now, this delivery robot is supposed to travel through city environments and navigate around by way of the bike lanes. And you might think that they chose that because it's a simple problem. But in fact, it's very challenging, and it poses a novel set of issues. Here, you see we're driving around. You think that you're just going to stay in a bike lane. But you have to go through construction zones. There's lots of obstacles in the way. A lot of unexpected things are happening. Car doors are opening. Pedestrians are moving about erratically the way they do. All the while, cars are zipping by on the side, and you have to avoid all that stuff. So here, Vayu is manually driving the robot around a bike lane in a small loop, and what they're doing is they're collecting data so that they can feed to their model. And what you're seeing here is the planned trajectory is there in blue. So they go out and they collect all this data. They come back, they train their models, and then they try to see, is it giving me the proper planned trajectory? Now, in order to do this, as you might imagine, they have to send a team out there with this physical robot, drive it around, but they have to set up any sort of interactions they want to take place, reset the test, and iterate several different times just to get enough data over several trial runs for whatever sort of interaction they're trying to test. And this can be very time-consuming and costly. So other ways they can be costly is the hardware isn't very reliable, and you can't collect data faster than real time. That's really the big issue here. Is you need to be able to collect a lot of data really quickly, and you need a lot of variations. So the stuff isn't going to be varied. When they come back after a hard day's work, running all these different tests, they're not going to have data from 10 different cities with all these various conditions, weather conditions, times of day, different traffic densities and such. They're only going to have a small set of scenarios that have emerged on this one route during similar conditions. And they certainly won't have very much data for things like imminent collisions or other rare occurring scenarios. In order to get that, they'd have to spend an enormous amount of time and send their team all over the world collecting all sorts of data. It's just not feasible. So you need to have something that would allow you to be able to tell when a new build comes out how it does in all the scenarios that you already know about. And you don't want to spend a lot of time, and you don't want to spend a lot of money to get it. So that's why simulation is so important. They want to be able to train in different cities, develop with different road networks, different buildings in the background, and different times of day with different vehicle and pedestrian interactions and so on. And they need to be able to collect a lot of data. See, what happens is when these robotics companies, robotics engineers, data scientists, what they're doing is they're trying to collect a lot of data. They're trying to see how their model is going to perform. And when they see that, they're able to identify gaps in the data. Okay, and then they want to generate data to fill those gaps with, it has to be very high quality data that they can then use to iterate their models towards the ultimate goal that they're trying to achieve. But they need to be able to collect this data in a way that allows them to iterate. So other types of robotics companies might be hearing this. Maybe not people that are developing delivery robots, but maybe mining equipment, farming equipment, factory equipment. And you might be saying like, well, this isn't some sort of unique workflow to value and delivery robots. We are interested in different parameters and different data ultimately, but the workflow is very similar to what we want. And you're absolutely right, and we hear you. Simulation does indeed allow you to achieve a workflow like this, and Vayu knew they needed simulation for all these different benefits, but they were running into some issues that are all too common when they look across the landscape of all these available off-the-shelf simulation tools. And so here are the different shortcomings that you can see when you go out and look at those things. The first one, the approachable tools, right? Like when robotics engineers and data scientists first think, hey, we need to generate all this different data, of course they're going to think about game engines as one potential way of doing this. These things are popular. There's reasons why all these different companies are using them. So they immediately get gravitated towards Unreal Engine as an option. But as I've seen in my time in the autonomous vehicle industry, and my partner Pete has as well, at several different companies, these robotics engineers and data scientists are immediately turned away when they get to Unreal. They start using it, but then they see that there's a lot to learn here. Unreal is not an easy tool for someone from a completely different industry. It's a completely different world to them. Their tools are entirely different. They want to make Unreal behave the way that they're used to, and they're just not able to do that without going through such a learning curve. So I've seen in my time in the autonomous vehicle industry, these data scientists and robotics engineers will actually turn away from Unreal after using it for a while, and they'll build a simulation engine from scratch, from the ground up, just to make sure that it feels familiar to them. That's how far they're willing to go. And at Tempo, we think that we can bring people back to Unreal by making things simple. And we're going to tell you about that a little later. Another issue, though, with simulation products off the shelf is that it's very difficult to create environments for the data scientists. So if you have an approachable set of tools, something familiar, you want to be able to generate maps. In this case for ValueSim, they want to be able to generate cities and stuff. But you want to be able to do it in one tool. You don't want to go around using several different tools as part of a map creation pipeline. That just gets back into this unfamiliar nature thing. The pipelines are brittle. There's a lot to learn. There's a lot of different things you have to learn for using all these different tools. It's just not a nice experience. Now, performance is something that simulation products do focus on, but they focus on it from limited knowledge. They don't know about all the different use cases that this thing's going to be used for. And as a robotics company, what you need to do is make sure that your use case, that the simulator is optimized for your use case. So you need to check that out. It might be difficult actually to see how this thing is going to perform for your use case, but the point is that any kind of inefficiencies there are going to cost you money, because the compute that you spend in the cloud when you're training and testing, you want all that to be focused on your just on your model. So you don't want to spend a lot on the simulation portion. You want simulation just to be a small sliver of that. And finally, fidelity. If you, it's more than just the look of everything. Okay, so the look of everything is very important. And when you have different sensor modalities like cameras and LiDAR and radar and stuff, what you mean by high quality sensor data is a little bit different. But it's more than that. It's actually the behavior of everything as well. So you want everything to give you realistic data through the sensor modality that you care about, so cameras and LiDAR and stuff. But you also want the behavior of all the agents and such in your environments so to be of a high fidelity, so that you can bridge the sim to real gap. That means that when you train your models in simulation, you want them to learn something in the simulated data that can be immediately applied to the real world application that you're going for. So Vayu had a tall order. So they came to us at wanting procedurally generated cities, large scale, with lots of different agents. That means vehicles and pedestrians and cyclists, flowing throughout the city naturally. And they wanted it all with a slick Python API so that they could do their work in a familiar environment. And they wanted it fast. Well, that's where we come in. We're Tempo Simulation. And we solve simulation problems. My name is Giovanni Pasteris, and this is my partner, Peter Malik. You can see him on the screen, and we'll introduce you to him later. I've been in I started my career in the game industry. I was in there for 13 years, and I'm pretty proud to say that one of my achievements there was working on the AI for Elizabeth from BioShock Infinite. I then went and spent the last 7 years working in simulation, where I led the core simulation team at Uber, where we were focused on robo-taxis, and that's where I first met Pete. From there, I went on to Aurora, where we worked on autonomous semi-trucks. And I'm also an adjunct professor at the Entertainment Technology Center at Carnegie Mellon University, where I mentor grad students with their ambitious and inspiring simulation projects. Pete has a background in robotics and hardware, and he was actually involved in designing and developing a sensor harness for one of Uber's early autonomous vehicles. From around that time, he started to transition more into getting involved more with the simulation projects, and quickly learned that testing software with software was the way to go. And pretty soon he was all in on simulation. And he started developing a simulator at Uber without using a game engine. So actually, he was one of those people from that culture that was trying to turn away from something like Unreal to make something more familiar with for all the other engineers to use. And that's around the time that I met Pete. That was 7 years ago, though. I told him at the time of all the different benefits that could be had by using something like Unreal for hardcore simulation for real-world applications. And since then, Pete's been on a real tear. He's made numerous Unreal-based simulators at companies large and small, at places including Ike and Apple, to great effect. Pete and I have stayed in contact over the years, and we're always checking in on each other to see if it's time. And I'm happy to say that earlier this year, it was time. We founded Tempo Simulation so that we could take this forward and develop what we believe is the right way to handle simulation in a game engine and give them the tools that they need. And we were very fortunate to come across very early on VRobot, who was in need of a custom simulator just like that. So I told you about this tall order. Okay, first up on the tall order that VRobot had was that, like all these other robotics companies, they want to have an approachable set of tools. So one of the first things we did at Tempo was develop the Tempo scripting API. And you can see it on the screen here. This is literally all the touch points necessary for defining how to import into Python and call this pause functionality and have that take effect in the simulator. And this is there's nothing special here about the pause logic. These are the touch points for any sort of functionality that you want to expose to Python. What you do is you just define your service and RPCs in Proto, and what that means is, for those of you that are unfamiliar, protobuf is Google Protocol Buffers, which is an interface definition language. So you basically go in there and define services, message types, and you're allowed to have structured data that you can pass around. Well, there's a wrapper around that called gRPCs. That's for remote procedural calls using the protobuf as a transport, and or rather the message language. And so here we're defining the time service. And all we have to do is say that there's an RPC called pause. We're calling it pause, and it takes nothing. So we're passing a request with no real data, just an empty, and it returns nothing. It just has to pause the simulator. Then in your header file somewhere, you just have to import from tempo itempo scriptable, which then you have to implement a function called register scripting services. From there, all you're doing is mapping handlers, request handlers, to the C++ side logic that you want to run when the request comes in. So you're just using a bind. And then down in Python, you're able to import the tempo libraries and then use them with something as simple as tt.pause. But there's something important here. Did you see what just happened, though? What we did was we made it easy for our users to stay in Python, because what we're going to do is we're just going to keep making this API richer and richer and allow them to have access to everything in Python. But further, if they do have to go in and modify something themselves, they can just get in and get out. They don't have to spend a lot of time dealing with boilerplate and other frustrations like that. So Vayu not only needed the simulator to talk to Python, but they also needed it to talk to their robotics middleware, which is ROS. That's a robot operating system. And you can see this visualization tool for ROS at the top, and the Unreal third-person sample down below. But we've augmented the sample with a few things so that it can communicate to ROS. I'll run it here. You'll notice that as the mannequin moves around, you can see a hierarchy of transforms moving around in the ROS visualizer. And when the cubes are kicked around, you can see their transforms reacting up there as well. It's pretty cool to see the model just as a bunch of transforms moving around. What this shows, though, is that we're able to communicate from one simulation world to another. And this allows our client, VRobot, to do hardware in the loop testing. So with the robot OS running natively on the delivery robot, they're able to see the behavior of their software running on the native hardware rather than the software running in the cloud when it's communicating with the simulator. So that's really important to understand what it's actually going to do before you let it do it in the real world. Now, another important thing here is that these two different simulated worlds here, the ROS world and the Unreal world, the tempo simulator, they need to agree on time. And so we've taken great care to make sure that Tempo ROS and Unreal, or through Tempo ROS, Unreal and ROS can stay in sync and agree on time. There's actually two time modes. Real time, where the simulator runs with the wall clock, and fixed step, where the steps are you define how many steps per second you want, and you can step through individually each frame. Now, under the hood, it uses a fixed point representation, so there's perfect precision. And another feature is that if hardware and software allow, you can step your simulator faster or slower than real time. Just a quick point here, Tempo ROS even has blueprint support. That means that you can use blueprint to publish to ROS nodes and subscribe to ROS messages through the nodes, just right from blueprint. So if you wanted to do something quick, you wouldn't have to go through all the effort of doing anything in C++, and some people might like that. Again, we knew we needed to leverage existing technologies wherever possible. Otherwise, we would never be able to make this work with just two people. It's just me and Pete working on this. So that's really the whole point of this, is that we need to look over the landscape of all these different tools. In this case, for the environments, we needed to find a tool that allowed us to create as much of a full-scale city procedurally as we could, so that we only had to augment just a little bit to kind of make it what value needed. So luckily enough, we found a company called Worldbuild, who was just about to release their first version of their product, Citybuild, which did pretty much everything we needed out of the box, with a few exceptions. The timing was perfect. The tool was coming out right at the start of this contract. And what you can see here is something fairly beautiful. This is a full-scale city being created in their tool, and the final results of it. It's an artist tool, so it's meant for a user to just lay out all these road networks, tell it kind of what the road configurations are, what types of buildings do you want where. You can define districts, which kind of tell high rises and small houses, where they should be to make sense. They originally only advertised that they supported Windows, but we were able to port it to Linux and Mac pretty easily. In fact, we got to know the Worldbuild team pretty well early on, and gave them our patch that we used to port it to Linux, and they graciously accepted that. And I'm not sure if they officially support it, but they did make those updates to allow it to run on Linux and Mac. The Citybuild did have some parameters for lane lines out of the box, but that wasn't enough for what we needed for value. We needed to take it further, so we kind of rehauled that and added the ability to tweak many, many more parameters for the lane lines, and especially for the bike lanes, because that's one of the primary features that value needed. So you can see those kind of being tweaked around right here. But it's not enough to just change the values and change the look, because we need vehicles to be able to drive on these. So no matter what combination of parameters you put in there and lane configurations you come up with, we need the vehicles to be able to automatically drive on there. So we need some sort of procedural lane graph as well. Well, we chose to use Unreal's Zone Graph plugin for this. And here, as you dial in your parameters, all of those will influence how the zone graphs are to be generated. And naturally, if the roads are procedural, then the intersections somehow need to be procedural too. That, at least insofar as like what lanes are allowed to connect through the intersections to other roads. So now that we have the ability to generate these roads and intersections in a procedural way, we need to make it easy for our client to go about exploring the space of variations and such. Like, we don't need them to come into the tool and explicitly lay these things down like an artist would. So we need them to be able to do this in their own environment, like we were talking about. So in the same tempo scripting Python API, they're able to run some logic that allows all these parameters to be filled in, and generate this by sweeping through a ton of combinations of ranges of acceptable parameters. And so what you see here is the lane lines and the bike lane positions and such are varying. The buildings are kind of being regenerated. You can see even some trees and traffic light, or what do you call it? Street lights changing around with the changing roads. And this is all done in script. Like no one's actually coming in and tweaking this. This video isn't hiding that. What this is a script is running and generating this right there in the editor, and we're just filming it. Value's robot uses cameras for its sensor, so that it can detect obstacles and plan its path. And they needed what they were looking for is a way to produce lots of camera sensor data so that they can have ground truth labels and ground truth depth to start with, so they can reason about what they're seeing in the scene just through cameras, and then eventually plan their trajectory to drive. And so we need these vehicles to make the city come alive. And one of the things we did early on was we planned to use the mass traffic vehicle agents from the city sample demo, because they're amazing and they pretty much do everything we need out of the box. And that's why we made the choice to generate the zone graph instead of some other sort of lane graph, is because the city sample vehicles from specifically the mass traffic agents, they only need the zone graph in order to pretty much do everything we want. That means like drive around these roads, queue up behind each other. They navigate intersections properly, whether it's stop signs or traffic lights. And we only needed to make a few modifications after that. Some of them are here. We added some yield behaviors like reactive yields and preemptive yields, and the ability to filter lane connections at the intersections, but in the project. So we had to make some modifications to the zone graph plugin to allow us to bring all that logic into the project. But it wasn't much to it, so we were able to get a lot for just a little bit. Just generate the zone graph, and we got all these vehicles driving around. So here is an example of that. The look of everything is one thing, but you need it to behave a certain way, and that's what this is all about. So the vehicles are the mass traffic agents. They're able to behave this way because of the zone graph, like we were saying, yeah. We'll just let this play out for just a second so you can see. There is a yield behavior right there. As one of the bikes was trying to go through the intersection, one of the vehicles stopped as it was turning right and let it proceed before it continued. What we can say here is that after we've taken care of all this stuff, we have the finished product. So this is ValueSim, and that's the Value 1 delivery robot right there. In its natural habitat, navigating through cities in the bike lanes. But this is a virtual world. Okay, so how does it really work? Are they able to train in the simulator and get this to work? Will it transfer to the real world? Well, let's take a look. So check out what they were able to do with Tempo. They were able to train on just simulated data and have their models learn to produce the semantic segmentation. That's the labeled images, and using Tempo's ground truth for the labels, as well as the depth using Tempo's ground truth for the depth data. And so you can see as these label images, where what you're seeing here is all the vehicles are one color, all the lane lines are one color, pedestrians are one color. They're fading in over the top of these images from their simulated data test set, and they're mapping up really well. So you can see as it fades in, the garbage can there and the sidewalk and the lane line are mapping up really well to the simulated data. And what we see when the depth images fade in is that things in the foreground are red, whereas things that are far away are blue. So everything looks very convincing there. But that's just in the simulator. You have to take it into the real world to see if it transfers well. So here is now some real world images. We need to see if what it learned in the simulator is able to transfer. That means what we should expect to see here is that when the labels fade in over the top, that they map up to the lane lines, to the vehicles, to the pedestrians, and so on. So let's take a look and see if that happens. And it does. So they were able to train in simulation with no fine-tuning whatsoever and achieve this understanding of a scene in the real world. So they're able to tell where the vehicles are, the lane lines, pedestrians, trees, and so on, and get a pretty convincing depth understanding as well. But that's just understanding the scene. Now you have to make the robot drive about the world. So let's start in the virtual world, right? So now they're going to drive their vehicle here. And this was trained just in simulation. You see the green is the left lane boundary, the yellow is the right, and the red is the planned trajectory. So in simulation, the Value 1 robot is driving around collecting data, and when their model trains, this is the result. It looks very convincing. The green and yellow are tracking the lane boundaries, and the red is indeed giving a realistic planned trajectory. But this is just the simulated world. I will say that where we go from here is if we encountered any issues, we go back to what their workflow needed to be in the beginning, which is they generated this data, they trained, they found some issues, so they identify gaps in their data set, and then they just ask the simulator to generate more data to cover that and retrain and iterate that way. And they will see their model iterate towards perfection and the goals that they have. So now we take it into the real world, and incredibly, just training in Tempo Simulator with no fine-tuning, the same model that was driving in the simulated world, that learned how to drive in the simulated world, is now able to show a reasonable planned trajectory for all the chaos that can ensue in the real world here. Again, the red is the planned trajectory. It goes around the cones. It tries to avoid pedestrians jumping out in front of them and such. So the answer is that it transfers to the real world pretty well. Did we really develop a simulator in just 6 weeks? Yes, we actually did. We delivered a simulator to Value with procedural city generation, road and bike lane parameterization, and the comfort of the Tempo scripting API in just 6 weeks. Now, at the time, it wasn't finished, but all the features came online following the 80-20 rule. And that means that we were able to showcase to our client working features, such as going from no agents whatsoever in the city to agents driving around, performing almost all of the functions they needed to do very quickly. And they were able to see the effect and the potential of where we were going with this, and then we just followed up by making everything more robust. And the only reason we're able to succeed, look, we're only 2 people, and the only reason we were able to succeed is because we made smart technical decisions based on our experience, and by leveraging all of the technologies like Unreal, mass traffic agents, the zone graph, and other plugins, as well as some third-party stuff like Citybuild, and we were able to get a massive head start. Now, we didn't just come here today to talk about all the cool stuff we made and show you how our client benefited from it and that sort of thing. We actually came here for something else. We came here to tell you that you can have Tempo too. we are releasing it as open source under the Apache license version 2.0, which is a very permissive license. You can modify, distribute, and use it for commercial purposes, and you can have it for free right now. This has been our plan since day one. That's to release Tempo as open source, but then continue releasing Tempo-owned source code that we developed during our contracts, so that all of our previous clients can benefit and all of you can benefit as well. Oh, but there's just one problem though. See, as part of our contract with Vayu, they own all the procedurally generated tools that we built on top of Citybuild. So without those tools, we wouldn't have a virtual world for you to experiment with our sensors and agents and scripting system. So that would be a shame, right? That's why we went ahead and built you a nifty demo anyway. So what we have here is a demo integrating Tempo with Cesium's 3D map streaming tile streaming. And the 3D map data comes from a company called Aerometrics, who produces very high quality photogrammetry models of cities and integrates them with Cesium. So this here is some of their free data. It's Denver, Colorado. And so we chose to build our demo simulator right there. It's a simple demo, but it showcases all of Tempo's main features. So we have all of the Tempo agents using the mass traffic framework as the foundation. So you'll see all the vehicles driving around behaving as such with the additions that we added. You have Tempo's real-time mode and fixed step mode, and you'll have the access to Tempo scripting, which allows you to expose things to Python, so you'll be able to control, let's say, the time of day. All the vehicles have Tempo cameras, which means all the vehicles will have Tempo cameras, and you can stream the color, depth, and label just like the Vayu is doing in Python. And now, a quick message to aspiring simulation engineers. There's never been a better time to be a simulation engineer. All you have to do is leverage foundational technologies just right, and you can do almost anything in short order with just a small team. And for everyone else, call Tempo, let us help. Yeah, take a look here. So vehicles, these are the mass traffic vehicles driving around. Really nice looking data here from Aerometrics of Denver, Colorado. We're jumping around to the different vehicles. You can do this yourself when you download. You just hit tab. You can jump around to different vehicles, and from there you can run our scripts and then extract the color, label, and depth images, and you can have them all running simultaneously if you wanted. But yeah, this is the demo we put together. You're able to experiment with a full suite of tools that we made for Vayu, minus the procedurally generated city, and we hope you enjoy that. So we'd like to thank VRobot for being our first client and for the opportunity to build a custom simulator for them. Worldbuild for the amazing procedural city building tools to serve as part of the foundation for ValueSim. Epic for having us here to talk today. Luke Schmidt for designing our website, our slides, and our t-shirts. And all of you for attending our talk, even if you're just watching this on video. Go download Tempo. Go download the Unreal Fest demo. Come say hi to me and Pete, and we'll see you around. Thank you, but I'll stay up here for questions.